Okay, today we will start from resonance, which is part 2 of chapter 5. Okay, resonance describes the phenomena of increased amplitude that occurs when a frequency of a periodically applied force or a Fourier component of it is equal or close to the natural frequency of the system. Okay, so we have to remember that it is close to or equal to the natural frequency of that system. Okay, so when an oscillating force is applied at a resonance frequency of a dynamic system, the system will oscillate at higher amplitude. Okay, so at resonance frequency, if this force is applied, the system will oscillate at higher. So at resonance, we'll get higher amplitude than when the same force is applied at other or non-resonance frequency. But if you apply at resonance frequency of that given system, so the system will acquire the maximum amplitude. Or you can, there is oscillating of a certain object can be an example, example of this system. So resonance is the increase in amplitude of oscillation of an electric or mechanical system exposed to a periodic force. So just like pushing of a person or a child on sitting on oscillating object. So if you apply a periodic force whose frequency is equal to or very close to the natural and number frequency, then that one will acquire the maximum amplitude. Okay, so resonance is a phenomena in which external force or vibrating system forces another system around it to vibrate with greater amplitude at a specified frequency. The frequency at which the second body starts oscillating or vibrating at higher amplitude is called the resonance frequency of the body. The basic example of resonance can be observed in various musical instruments, or you can take this tuning fork. So when you make this tuning fork to vibrate, so if you have a number of tuning forks next to it, so only tuning fork with the same frequency as the original tuning fork, this one fork will vibrate and give a response. The other will not give a response. So the one which have the same frequency of the original fork will vibrate and give a response. Okay, this can be expressed just like in our day-to-day experience. From our day-to-day experience, if someone calls another person with the name Mr. X, so you can't give any response. But if someone calls Mr. Y, say this is the name of the person, then the person will give a response immediately from day-to-day experience. Or as you can see, this is non-resonant, but this one is resonant. This one actually explain about the amplitude. So at resonance we get maximum amplitude. Okay, so a classical example of resonance is the swinging of a person sitting on a swing. Maybe a child or others. So a swing is a very good example of an object in oscillating motion. Initially the motion is very slow. The swinging is very slow, and the swing doesn't extend to its maximum potential. But when the swinging reaches its natural frequency of oscillation, a gentle push, a small push to the swinging helps to maintain its amplitude. Its maximum amplitude will be maintained by a small force of swinging all throughout due to the resonance. Okay, so in an ideal situation with no friction at all, even that the slight push will not be necessary once the swing reaches its natural frequency for it to sustain the maximum amplitude forever. But there is a consideration in swinging. There is a consideration of a resistance, and there is also friction on the pivot point. Blah blah. So many reasons are there. But if those are removed, therefore this one will continue oscillating with maximum amplitude forever. Also, almost all musical instruments like flute, guitar, it's work on the principle of resonance itself. Okay. The other subtopic that we have is the Doppler effect. The Doppler effect is observed whenever the source of waves is moving with respect to the observer. It can be described as the effect produced by a moving source of wave in which there is an apparent upward shift in frequency for observer towards when the source is approaching an apparent downshift in frequency. For elaborating of this Doppler effect, you can consider the siren from the ambulance or from a police car. So if this police car is going in the right direction, so there is you get a small wavelength, but the frequency is high. This person will receive a high frequency of this sound wave, but this one, which the police car is going away from her, and she receives a long wavelength of sound and a low frequency of this sound. So this is an example. So there is a formula for finding the V value of the sound source in the right direction as well as in the left direction. Okay, now for example, to get that formula, let's start from this. F sub naught is the frequency heard by the observer. F sub s is the frequency emitted by the source. In our case, you can consider a police car. V sub naught is the velocity of the observer. V is the velocity of the sound. Vs is the velocity of the source. Now, the frequency of the observer is equal to the frequency of the source multiplied by V plus or minus here. In this case, you have to consider either plus or minus. When to use plus and minus? Now, take this example. The upper side, this is the plus side, we use refer motion of one towards the other. For example, a person and the police car approach to each other. In this case, when they approach to each other, in this case, we use in the upper one, we use plus sign. In the lower one, we use minus sign. But if one go away from the other, or the police car and the person, they go away from so in this case, we use a minus sign for upper side, and plus for lower side. So V is the velocity of sound, V sub naught is the velocity of the observer, V is the velocity of sound, V sub naught is the velocity of the source. So with this formula, you can find the frequency, that is the frequency, look here, the frequency received by this one, the frequency received by this one, the frequency received by this one. For example, as you can see, the person here is receiving higher frequency, and the person here receiving lower frequency. You can let's go back to the formula. Why this receive a higher frequency? Why she receive lower frequency? It's possible to explain using the formula. In this case, one is approaching the other. So the police car is approaching this person. So in the formula, when one approach to the other, we use a plus sign. So V plus V naught and V minus Vs, because one is approaching the other. So we get a larger frequency. The observer receives larger frequency. But for her, we use a minus sign, V minus V naught. So it decreases the observer frequency. Then this one is higher, this is lower value. So for this, you get a lower value of frequency heard by the observer. She received a lower frequency, but he received the higher frequency. That's we understand from this Doppler effect. Okay. The other one is in 5.5, we get the characteristics of wave. So waves are important in determining the size of waves, the speed at which they travel, how they break on shore, and much more. Following are some of the characteristics of wave. The first one that we have is reflection of wave. This is an example of reflection of wave. So in this example, this is the incident wave, and this one is bouncing back on the surface and reflected in this way. So whenever a traveling wave reach a boundary, this is considered to be a boundary, part or all of the wave bounces back. So this phenomena is called reflection. This is an example of reflection of the incident wave on this boundary. Okay, the other one is refraction. It is a change in direction. In this case, there is a change in the values of v, direction of wave passing from one medium to another, caused by change in speed. Therefore, this is the incident ray. So it refracted when it approached this surface. On this surface, it refracted, and this is a direction, but here it approached to this normal. This is a normal line, and it is near to the normal, not away from the normal line, due to the change in index of refraction. So due to the change in index of refraction, we get a different v value in the upper side and in the lower side. As you can see here, the n value of the lower medium is greater than the n value of the upper medium. Due to this one, the wave is refracted towards the normal. So the speed of sound wave is greater. The speed of sound wave is greater in warm air. So the speed of sound wave is greater in warm air than in cold. Okay, so this is also an example. This is the wavefront, the incident one, and then after refraction we get this one. So as you compare theta 1 with theta 2, theta 2 is less than theta 1 if this one have n value greater than the upper one. Okay, so the other one is diffraction of a wave. It is the spreading of a wave around the obstacle. This is the wavefront, this is the obstacle. So when the wavefront gets this obstacle, so there is a spreading of wave. So the spread of wave is in all directions, in this case, in this direction, and this direction, and this direction, and this direction. But this one is only one direction. But when it gets this obstacle, so there is spreading of wave. This is called diffraction. It is a spreading of wave around the obstacle. Diffraction takes place with sound, with electromagnetic radiation, such as light, or it's possible to get here in X-ray, gamma ray, and with very small moving particles such as atoms, neutrons, electrons, which show wave-like properties. These electrons show wave-like properties. So you get also diffraction, and there are instruments that work with electron diffraction. Okay, this is the second. This one shows actually diffraction by two-hole. So this can be used in Young double slit experiment in order to study the wave properties, and as well as the wave properties of light can be observed by this double slit experiment. You get interference on the screen. You place a screen here, and you get maximum, minimum, maximum, and minimum. This shows the wave property of a wave. One of the properties of the wave is just interference, that is constructive and destructive. It can be observed here, constructive and destructive, by bright, dark on the screen. You can place the screen here, and you get bright, dark, and this can be easily done in the laboratory. Okay, so the 5.62 image formed by lenses. Lenses are commonly used to form image by refraction in optical instruments such as cameras, telescope, and microscope. A lens is an optical system with two refracting surfaces. The two types of lens that we have is convex lens and concave lens. A lens is part of transparent thick glass which is bounded by two spherical surfaces. It is an optical device through which the ray of light converges or diverges. There are enormous applications were there by using these lenses. So this one is a convex lens, so point. So the other one is concave lens. So, and this is the image formed by convex lens, and this is the image formed by concave lens. So this image is really inverted, as you can see here. This is a focal point. So parallel incident ray refractor passes through the second focal point. Look, this one a parallel line as compared to this line. This parallel line, and after it passes this length, it passes through the second focal point. That's we get from 1, 2 sides, rays through the center of the lens. This ray, which is shown by green line, center of the lens, does not deviate. Just like the other, it cannot deviate. It goes just like following this straight line. And the other one, rays through the first focal point, focal F1, and then that emerges parallel to this axis. After it approaches, after it passes the lens, then it will be parallel to the this one axis, parallel to this axis. So the other one, then this one concave lens, the first one, parallel incident ray appears. This is a parallel incident ray, appears a refraction to have come from the second focal point. This is the focal point. This is the first focal point. Then it appears that it comes from this point. It comes from this point. And the second one, 2, which is says ray through the center of the lens, so does not deviate. This ray, which is shown by green color, its ray does not deviate. It continues following this straight path. The other one is ray aimed at the first focal point. This is a focal point, and we follow this from this point up to this point. If you draw this straight line, imaginary line, so this ray, after it passes through this center, the lens, it will be parallel to this axis. So ray aimed at the first focal point. This is the first focal point, F1, that emerges parallel to this axis. So with this, we can find the position of the image format and the edge value, the height of the image, following these 3 lines in case of concave lens and as well as convex lens. Okay, the equation related to the image distance, object distance, can be calculated by this one. 1 over object distance plus 1 over image distance is equal to 1 over the focal point, 1 over focal length. You can take F1 or F2. They are equal, no problem. The other one is the way of finding magnification, or is by using height of the image and height of the object. So magnification is the height of the image over the, if they are equal, no magnification. If this one is 2 times object, so magnification is 2 times. Make magnification as the ratio of the image, height of the image to the object, or ratio of the image distance to the object distance, also possible to get the magnification. Okay, we need to stop part 2 here. Part 3 will be continued in the next video. the period is equal to 1 over 1.67 or 30 divided by 5050, which is equal to 0.6. So this 2 seconds is not correct. So have a correction. It